Hi, everyone. My name is Nikola, and I'm an Oberassistent or senior postdoc at the chair of computer-aided architectural design or digital architectonics. How is it called now? And yeah, I'm at ETH for almost 10 years doing research which kind of encompasses these three topics. One is architecture, one is modeling, and one is computation. There's a lot of work that I did on this topic. So what it is about is that when we think about these three topics, architecture, modeling, and computation, and we think about what kind of interrelations are there, my hypothesis was that these three things are intertwined in a way which only covers a very small portion of the spectrum of what is actually possible when we think about these three things. And my kind of hypothesis is that most of the models that we use as architects in terms of computation and modeling are very primitive, and that there is a huge space to explore, especially models which are I call communicational models, which are, as you will see in this course, something that is derived from the computational paradigms of the 20th century, starting from quantum physics and developments at the beginning of the century and ending now with machine learning, which kind of fully supports these paradigms. If you're more interested in this topic, I used to have a course that I taught for 2 semesters, which was more theoretical, the development of formal logic, computation, linguistics, and certain parts of analytic philosophy and quantum mechanics, and showed how and where architectural models belong to, and how can we kind of characterize the current developments, and what are the aspects that we have overlooked, and the direction that we haven't explored. And this is all summarized in my book, published by Werkhäuser. You can find it in the ETH library. So if you're interested, I recommend that you take a look. This is my GitHub. This is a place where code can be stored for free and shared with the world. I have this course as an interactive book, not really interactive, but at least animated book, which can be found on this address. So it's here. That's it. And then there is a repository called Machine Intelligence. And here you can see the course description, and you can see some files or notebooks. So the ones which have numbers in front, they are important ones. For example, this one, then Introduction to Derivatives. If you click on it, and there are, I think, 16 maybe of them. Maybe I put more. I'll change the courses as we go. So this here is code. The question is, what can you do? So you're not just a passive observer here. The idea is that you should run this code. How can you run it if you do not have Python installed, if you never coded in your life? How do you start working with these things? Well, there is a website called Google Colab. So you can just type Colab here, C-O-L-A-B. And the second link will be Google Colab. What Google Colab does is it's a kind of coding environment which is run on a virtual server by Google. So if you have a Google account, Google will make this virtual coding environment for you. It will initialize it. It will kind of simulate a small computer with a certain amount of memory and RAM and all of that. And it will install all the libraries in it. Everything that I use, it will be there. And you will be able to run my code on your computer, but actually it will be run on Google servers. So how do you actually run my code? It's actually very, very easy. You just go to my page, Machine Intelligence. You click on that. So I can just copy this link, yeah? Come to Colab, say GitHub here. I can just paste this link, yeah? And press enter. So do not exit or do anything else, just press enter. Then what Google does, it parses my GitHub repository because it's public. They can do it. I gave them the permission by making it public. And then you can see all of my notebooks. And if you click on one of them, for example, the first one, Google will replicate it in its own coding environment. So you will have your local copy. You can save it then and whatever. Change it. Yeah? You can change it. But the interesting thing is that code will become available for you. Yeah, some of them will be hidden because it's kind of different formats, so Google does not do it exactly the same as GitHub, you can always unhide them. Yeah. But when you come to code, where is it? Here. Yeah. So this is then this function that I wrote. And if I click here, I can run this function. And then Google will say, yeah, this might be dangerous, but run anyway. I assure you that it's not dangerous.
That's actually not
Yeah. So now we define this function s of t, and if I click now s of 5, it will give me 25, yeah? And then all of this code should work. It should work in all the notebooks, yeah? But yeah, just make sure that do not run this if you didn't run the one before, because it might be dependent on it, yeah? If we didn't define what interval is, like this code, then this one should not run, yeah? So you see all of this code, you can run it. Also, you can download my notebooks and then open them, install what is called Anaconda coding environment, and then just run them there, it will still work, yeah? The idea of the course, before I started showing you the links to inscribe, is that we as architects have certain difficulties if we are interested to learn contemporary computational models, such as, for example, machine learning as a kind of very large and important part of this of the computational world that we live in today, because the way how machine intelligence in general, machine learning, artificial intelligence is taught, does not match our profiles. So we are not engineers. We do not have 5 semesters of mathematics at the university where we could really nail these concepts, mathematical concepts down to the detail. You could learn calculus 1, 2, 3, multivariable calculus, matrix calculus. Then you go through all the linear algebra, vector spaces, and all of that. Then you go to statistics, advanced statistics. Then you go over, what else is there? Yeah, it doesn't matter. You get the point. You know, there's a lot of math that you need to cover. And then when you go and look at textbooks for example, engineers, you can see that you don't simply understand anything, that the notation is difficult, that the elements are difficult, that simply there's no way that you can master that. But then there's a kind of funny alternative offered from, for example, Google and Facebook. They give you their libraries, their software, like PyTorch from Facebook or TensorFlow from Google, and they say, yeah, machine learning is easy. Look, just download this library, install it, and look at this tutorial, and then you see how you can do things. But what I think about this is that if you start by using libraries and just doing these kind of tutorials, the range of topics and problems that you can address is very, very limited, first of all. Second of all, you're not really learning what you're doing. You're just doing it. And you're not learning anything about, for example, neural networks or deep learning. You're learning how to use Google's library. So you're a user. You're not someone who is intellectually involved with the topic. You do not know what's at stake. You do not know how does your architectural profession or any other non-engineering profession, how does it relate? How does it fit to the story? What can you expect? What will machine not never be able to learn? What it will be able to learn? So these things are kind of completely outside of your scope. And therefore, it's kind of difficult to proceed. People do not know what to do, and yeah, there's this easy path, there's this very difficult path, and nothing in between. So my strategy is kind of in order for me to understand it, I had a lot of time. I was working, I was paid to do this work and research. Therefore, I learned a lot of that math. And then I also learned what is not necessary to learn math-wise. Of course, it's very important, and if you can learn mathematics, do it. It will really be useful in your life. But the thing is that if you would like to learn machine learning, then you do not have to learn it all. You need to learn a couple of things, in my opinion. This is what I thought that are the most important things. And if you learn them well, if you know them well, only these couple of things, you will be able to understand everything which is going on. You will be able to really intellectually look at this topic, and you will be able to write, you will be able to explain to your friends, you will be able to really seriously discuss this topic and seriously think what does it mean to you and what it means to our profession. So my idea is to really teach you some basic mathematical ideas, some very important ideas from calculus. The most important one is derivative. If you know what derivative is, if you're comfortable with derivatives, not like, you don't have to learn all the integrals and Taylor series and all of these things. If you learn derivatives, you will get 1/2 of this course. You will be able to understand 1/2 of this course. If you learn linear algebra, if you learn vectors, if you learn matrices, and then if you a little bit sneak peek at tensors, which is kind of abstraction of that, you will be able to understand the second part of the course. And I, in my teaching and in my pedagogy, will make sure that you can understand these things. I will present them for a multitude of topics, from an algebraic perspective, from geometrical perspective, from harmonic perspective. I will try my best for you to understand these topics, not to be afraid of them, and to see them in a kind of new angle, which would hopefully help you to understand this whole course. So this will take maximum 3 classes out of 10, everything that has to do with math. The rest will be about machine learning and not so much about the code. Of course, code is there, code is online. So if you do not know how to code, this will not be, I think you can still really benefit a lot. And this is why I'm kind of introducing this kind of collaboration between math and coding for you to see how they are really closely intertwined. And how does this relate to these very abstract, important concepts such as derivative and, for example, matrices? If you would like to take the course, I would suggest you to go to this website. I mean, to type this address now, because this will take you to another address where the virus will erase all of your data. And no, you're just gonna get a Google Sheet where you can put your name in if you're interested to follow, so that I can really write you an email and know that you are following the course, so that I don't have to bother you if you decide to drop out. The test, so the outcome, what can you expect? You can expect to learn the math, you can expect to learn the concepts, you're gonna learn some coding, you're gonna have the algorithms at stake, you're gonna have them available, you will know how to work with them, and you will be ready then to use these libraries with full knowledge of what these libraries are made for and how you should use them, with the knowledge what they actually do, yeah? And then there will be a test at the end, and the students of the last semester, which were a lot, the 90 people started, 50 have successfully passed. So it's kind of, out of 60, let's say, that came here, 50 passed, and then I gave them some more chances to pass again, and then 5 more passed, and they have never seen the questions of the exam, so they just came and passed it. So it's doable, so don't be afraid. But yeah, there's maths, and this can be scary for architects, but yeah, again, I think we can deal with that. Okay, so let's now start with the topic, and yeah, the most important topic will be derivatives. Or, as I call it, calculus on a number line. You will see later where does that come from. And of course, I will start with the examples, and the great example is always something that you can relate to. One is motion. Because why motion? Because we need to think about not one variable. We need to think about something called functions. We need to think about functional dependencies, when one thing is dependent on the another, or when two things are kind of connected in a way which is kind of formalized. And definitely when you think about motion, what is connected is space and time. In general, if you think about speed, time needs to exist so that you can have knowledge about where certain object is at one point in time, and then knowledge about where the object is at this other point in time. So what we will imagine is that we have a bicycle, and then you need to go from the point A to point B. And yeah, this takes some time, and there are certain things involved. Let's see what things are involved. First of all is distance. So if we abstract from direction, of course, if you think about vectors as mathematical objects which tell us you can go from here to here, or you can go from here to here, we don't have to care about that at the moment. We can just think that from this point you can go wherever you want. And this, whatever you want, is a circle, and this is the radius, and this is distance, because distance is kind of abstraction from the direction. Okay. And now someone told us that these two things that are 300 meters away, you can now see it on the vertical axis, I rotated it, we passed this distance in 20 seconds. So this is all the information we know. So the only thing that we kind of know is the average speed of our ride, which is 300 meters per 20 seconds. And we do not have any other information about trip. So the only thing that we can express is a kind of average speed. And this is described by this line. Yeah, straight line passing through the origin. What does this line indicate? What can you read from this line? Well, the consequence of this linearity, of this kind of constant speed, is that you can either say, okay, I go 300 meters in 20 seconds, or I go 150 meters in 10 seconds, or I go 15 meters in 1 second. And of course, you can say 300 meters in 20 seconds, but the whole idea is that we would like to have a kind of more standardized way of describing things, and one of these is called rate. And rate means that this number that we divide needs to be 1. So we look at 300 divided by 20, we divide it, we get 15 over 1, or 15 meters per second. Okay, this is the so-called average rate of change, because there is change which is introduced by time. And now if we plot this, if we put two graphs next to each other, then we see that our average speed is actually a constant. It is a line which is horizontal, which means that any time during these 20 seconds, we have constant speed. But in reality, that's not, of course, the case. In reality, you cannot just instantly go at 15 meters per second unless you are already moving 15 meters per second, and then someone can just capture a few seconds of your constant motion. In principle, what you need to do to go from A to B is to, start from 0, then go at certain speed, and then like slow down and stop. Yeah, so go back to 0. Which then gives you what? It gives you curvature. So this red line now has some curvature, so it is not straight like before. But you can see still that the endpoints can be still connected with a triangle. And this triangle, it's a very important figure. We will have it all the time with calculus. This is the very important thing to notice, that this triangle is always indicator of certain average. But now, you see, when we have this curvature, there is some kind of acceleration and deceleration involved. Now the question is, if someone gave us this curve, and if this curve was actually a precise plot of our movement, so someone took like some device and recorded our movement, and then plotted our curve, since now we have kind of more data, what can we deduce from this? How can we talk about speed? Are there more ways to talk about speed? And the answer is yes, there are more ways to talk about speed now. What we can do is we can start subdividing our ride. For example, we can say, what happens if I don't have now only one triangle, but if I want to have more triangles? And you can see that on the left portion of the image. We subdivided the ride into 4 parts. And then we see that we have 4 triangles. And we see that these triangles kind of vary. Although this axis, which is time, is always the same, you can see that for the same time, this other axis, which is distance, can be lower or it can be higher. So, and then you can see that, for example, if for the same amount of time t, you have passed a very short distance, this kind of line, the diagonal, would indicate a low speed. So then this would be no motion. If this line is horizontal, it would be no motion, you're stopping. And if as you increase it, you increase the speed. If you go to this case, this is impossible. You cannot traverse anything in 0 seconds. But so it's something between these two things, yeah? So what we get by dividing this side with this side, what we get is we get more numbers. For example, for the first part of a ride, we get 5.4 meters per second, then 24, 25, 5.6. You can see that there is a kind of, we are subdividing the curve and getting more information about speed. And then what we do on the right is we subdivide in even more intervals. And then this blue curve, which tells us the speed, becomes something like a curve. Yeah? You can imagine that the actual speed might be a curve. But then the question is, okay, where does this lead us? How far we can subdivide, and why would we want to do this? So the whole idea, for example, of digital, as we know it, as we are taught to, for example, screens, is that everything is in principle discretized. So when you have a screen, if it's a 4K screen or HD screen, what happens is that you have pixels, which means you subdivide the screen into a certain amount of pixels in horizontal direction and some on the vertical direction. And you get a bunch of points, which kind of look smooth if you look from a distance. You know, if you go really close, you can see that they are just individual pixels. But you're kind of approximating things. So you have an image, you take it with a camera. This is kind of an approximation of what happens. And this is how digital technology works. And then the question is, okay, a parallel is, okay, yeah, I can now start subdividing more and more and more. Because if we imagine that curve is kind of continuous, we can subdivide, and then finally, we will reach something which looks like a real curve. But still it isn't, because it's subdivided, it's approximated. Let's talk more about that. So let's see about what approximation is, and what are the limits to approximation. Because limits to approximation leads to what we know as calculus. And the derivative is a concept which allows us to speak about infinitely smooth curve that will show speed. So how to talk about, in more general terms, about approximation. So let's see that we have this curve now, and then we zoom in to a certain portion of that curve there. And if you want to go more general, if you don't want to say, okay, I'm zooming at the location of 14 seconds, then you can introduce something called a variable. For example, t, and t is a number which can be 0, which can be -5, which can be 10, 15. So it's actually the value which is a placeholder for whatever value you want to put. So you can imagine, if you change t, then this zooming window moves across the curve. And then there are a couple of elements there. So first of all, let's say that we concentrate on the time t, and we would like to make an approximation of speed at that time. So on the x-axis, we have value t, and then we add something called an interval. And here, interval is just a small number, yeah? 0.001 seconds. But of course, you can parameterize that too. You can make it as big or as small as you want. But let's say for now, it's 0.01 seconds. And then you have two moments in time, yeah? One is at t, and one is slightly after it. And then for t, which is time, then we have another variable, because t can move. This means that what t crosses in the y direction, which is the output, which is the height of this curve, which is called s of t, or distance in terms of time. So distance for this time t is called s of t. And then there will be also a distance for the second point, which is going to be s of t plus 0.001. Okay, now we have a triangle. Yeah, let me just recreate this here. So just for you to not be confused about certain things, yeah? So we said this is t, yeah? If this is x-axis, so this is time. Actually, it's not x, it's t, yeah? T-axis, yeah? And we have some curve. And this is, for example, the origin. So this is 0, 0. So then this distance is an input of this relationship, yeah? So this can be 5 seconds, it can be 4 seconds, it can be 10 seconds. But we said, okay, we want to change it. So we're not going to fix it. We will say this is t seconds, yeah? So this is input, and this is output. So this length is output, this length is input, and this is s of t. Okay? Now we add another, so we now add 0.001, and then for this input, which is all of this thing, we get another output, which is s of t plus 0.01. And then just one thing to realize here, okay, this is output of the second point, this is second point in time, this is output of the first point in time. What is this? This is when you subtract the higher value from the lower value. This is the change in distance introduced by the small change in time, 0.01. So for the small change in time, of 0.01, change in distance in this. And this is simply s of t plus 0.001, which is this length minus this length, minus s of t. This is the most important image that you need to kind of somehow store in your head and think about. It's a very simple image, but that's the key of all things, yeah? Okay. Let's now give an example of this thing, yeah? Let's now see how, if we have some kind of curve or some kind of function, of course you know that functions can be visualized. For example, if you have y equals x squared, which is a parabola, which means that for input, for example, 2, output will be x squared, or 2 times 2 will be 4, then you know that this curve can be visualized as a parabola, yeah? So if you have here 1, then you will have 1 here. If you have 2 here, you will have 4 here, yeah? And now we just take 1/2 of it because we don't care about negative distances. Let's say they don't exist. Let's see how we can approximate speed for any input of time. So for anything on the x-axis, how we can approximate speed, yeah? Not distance. Here is time and distance. How we can approximate speed, which is a change of distance over the change in time. Okay. First, let's create a Python function, which takes as an input a variable t, and then returns this variable times itself, or t squared. So it's a very simple function. I'm doing it very simply, but purposefully. I'm not going to complicate things because I assume that you do not know how to program. And now, for input 1, of course, this function outputs 1. For output 2, it outputs 4. 5 times 5 is 25. Very simple function. You can see how it works. Okay, and let's say that we are currently interested in approximating speed for t equals 4. Yeah? So let's set it at 4. So now we want to approximate this function. Yeah? Distance plus a certain change in time minus the original distance. So practically what we are asking is dividing this thing, this distance, which is the upper part, with this distance, which is the lower part. So how do we do it? We introduce interval, for example, 0.01 seconds, and we say, okay, s of 4 plus interval, we're just replacing values, minus s of 4. Yeah? And now you get change in distance if you do it. And now we just divide it by the interval itself, which is 0.01. And you get 8.001 meters per second. Yeah? So we now approximated the speed at time equals 4 by using the interval 0.01 seconds. And we get something approximate almost 8, yeah? Close to 8. And now the main thing happens. What happens when we start changing the interval? We start from a very large interval, for example 3, which is huge, and then we go 2, 1, then smaller, 0.1, 0.001, and 0.0001, yeah? And then we just calculate the same formula, but for these multiple intervals. So this function will just go through all of these intervals and apply the same function, and then print for the time interval of interval. The average speed is, I assume, the approximate speed is speed. Yeah? When I run this, you can see a very interesting observation. So if the time interval that we add is large, you get the approximate speed about 11 meters per second, and then it goes to 10, 9, 8.09, 8.009, 8.001. So it kind of has a direction, yeah? It starts from something higher, but kind of starts slowing down, yeah? As you make the interval smaller, this thing kind of starts approaching a certain number, and this number is 8. If this is, for example, 4, so, yeah, x is 4, then the y, we start from a higher value, and then suddenly you can see this point here, which we move it as we make the interval smaller. So this is the interval. As we make the interval smaller, we can see this thing kind of quickly approaching this place, and then going slower, 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 slower. Yeah? And interesting thing is, however small you make this interval, 0.001 or 0.101, the output will never be 8. So there is inherent limit to approximation of things which are interdependent. You simply have a certain obstacle in this space that if you use 2 points to approximate speed, then you can never get it exactly. You can come as close as you want. So you give me a number of zeros that you want, and I give you the output, which is kind of close to the real thing. The question is there a real thing? Can there be a precise value of speed at that point? And this is really a philosophical question. So what happened is that these kind of problems were bothering mathematicians a lot, especially Newton and Leibniz at that time. And the question really is, what is the limit of this operation? How far can you get by trying to optimize better and better? This is the main question now that we think about. Considering that our time interval cannot be 0, what would happen if you would say that the interval is 0? What would happen with the speed? Someone wants to, has an idea. So I will remind you, if you approximate, we take a certain interval, and then we see the output for that interval, and then we divide the change in distance with this change in time, with this change of interval. So if interval is 0, if we divide this with this, what do we get? What do we get by dividing things with 0? What is 5 divided by 0?
Oh, it's
Exactly, you cannot divide by 0. Yeah? Exactly, so if you divide by 0, this does not exist in mathematics. It's impossible. So, if you ask, why did you just say that the interval is 0 and see what happens? You cannot. So, the question really is, considering that our time interval cannot be 0, what would be the best possible approximation of speed at any moment of time that you choose? So, the interesting question is, you can keep adding zeros until the end of time. You can keep adding zeros to this approximation for 100 years, and someone can do it in 100 years and 1 day and add a couple of more zeros and can make a better approximation. So is there some kind of limit between this thing being so small and between this thing being 0? So that's a very, very interesting kind of philosophical question, not only mathematical. It's like, how can we construct something which we know what we want it to be? So we know some kind of abstract properties. We want it not to be 0, and we want it to be smaller than anything that anyone can concretely specify. How can we design this thing then? And Newton and Leibniz figured that out, and this is what brings the idea of infinitesimal. Okay. Of course, this also then introduces various paradoxes, because if we think about speed as an average rate of change, so which means that there are 2 points in time, and then in order to have change, there needs to be 2 separate moments in time, because otherwise there cannot be change if the time hasn't passed. But somehow, if we are able to construct this thing, which is larger than 0, but smaller than any feasible measurement that we can ever make, then this would introduce a new idea about motion. So this would introduce a motion which can be defined in a single moment in time, singular value of speed, or so-called instantaneous speed. So very interesting things going on here. Okay, so how did Newton and Leibniz do it? So to find this best approximation, if you remember here the interval was 0.01, and then we changed it in our code. You cannot anymore now use any concrete number to represent this interval, yeah? You cannot use 0.01 or whatever number. So it cannot be a number anymore. So we first need to turn it into a variable. So it needs to be something that can change, but that's not enough, yeah? For historical reasons, we will indicate this new quantity. If the interval is time, then we will call it dt, d time, yeah? And this indicates this is a kind of special variable. It's not just a normal variable, otherwise it would just be t, yeah? And what is the property of this variable? It is that larger than 0, but smaller than any kind of number we can specify. Yeah? So it's virtual, it doesn't exist yet. We're just saying what we want to have. Okay? And now we have two values of time, t and t plus dt. And then you have the corresponding change in distance, which is s of t for the first point, and s of t plus dt for the second point. Yeah? And to compute the speed around the point t, we just need to divide the change of distance, which is this green thing, which is the green line, with the purple line. Yeah? S of t plus dt minus s of t divided by dt. Yeah? Divide with this quantity, which is virtual. And this almost allows us to compute the best approximation of the speed. But we are not there yet. This formula is not correct. Because there is something more to this dt, you know. There is a reason why we put d. Yeah? It's a kind of dynamic variable. Yeah? In the sense that we can imagine that this value moves towards a certain value. Yeah? So what we need to imagine is that our intervals that we specified with numbers now need to always getting smaller and smaller. Never stop moving towards 0. Yeah? Because this will improve the approximation of the speed. And the true derivative of speed in this picture is the ratio between this green line and between the purple line as they are shrinking towards 0. So it's a ratio between two things which are moving. So this is very interesting. So they're not fixed at any point of time. They're always dynamic. And it is the ratio of these two kind of dynamic things. Problem is, in mathematics of the time, there is no way to speak about this thing. Yeah? There are no symbols, there is no mathematical apparatus that can help you to speak to describe this thing. Yeah? You know, kind of have an idea, but you do not know how to describe it. Yeah? You cannot. How can you explain it to your colleague if you cannot do it in this mathematical notation? Yeah. So what you could do, you could use language. So you can say the derivative of speed at the point of t is this ratio of this green line and purple line as dt approaches 0. So if you say that, then you're correct. That is what is happening, yeah? You have an intuition. But the problem with mathematicians is, a mathematician would instantly ask you, what does it mean to approach 0? Tell me what does approach mean in mathematics, yeah? And the precise definition of this idea of approaching something was defined in 1821 by Cauchy and Weierstrass, and this introduces a concept called a limit, yeah? But don't get scared with these limits, don't get super annoyed by this definition now. It says exactly the same thing as the thing above. Instead of saying, yeah, it's this ratio of green to purple as dt approaches 0, you can also say the derivative is a limit of this expression as dt approaches 0, yeah? There's nothing special about it, it's just a formalism. Yeah, the whole idea is that there are these two pictures that you will see. One is an intuitive one, which I invite you to really master, because I'm okay that you are describing certain things with languages. We are not mathematicians. So it's okay if you understand what the derivative is in this sense. There is a ratio of these two things as the lower one approaches 0. So for me, this is fine if you understand it like that, because it is correct. On the right side, we have a very formal definition. And I will try to describe what derivative is from both perspectives, yeah? Let's try with the left approach first, yeah, this side. So the true derivative of speed at any point of time t is what this ratio of green or purple approaches while this dt, or the lower part, the purple part, is approaching 0. So it's about what one thing is approaching while another thing is approaching something else, given that the second thing is dependent on the first one. As you can see, it's quite an intricate idea, and requires you to practice mentally, not to write formulas. It requires you to think about it, you know, what this thing is. To imagine it in any way that is good for you to imagine things, yeah? Derivative is not this ratio. Derivative is what this ratio is approaching. So derivative is not about this is black, this is blue. Derivative is the question. When someone asks you what is the derivative, he's asking you, she is asking you, what this ratio is approaching, not what it is. Yeah? I will finish in 1 minute. And if you want to say precisely, because in mathematics you need to say what something is, if you need to say what derivative is, not what is approaching, then you use the second side. Then you can say the derivative is the limit of this expression as dt approaches 0. So derivative is the limit of this ratio, or derivative is what the ratio is approaching as dt approaches 0. Yeah? And then there's one more thing just to note. You remember this dt, that is a kind of special variable which shrinks? Well, with limit notation, limit takes this special thing and takes it to itself. So instead of imagining dt to be some special variable, you can imagine that limit now takes care of taking any variable here and making it so that it shrinks. Yeah? So instead of saying s of t plus dt minus s of t divided by dt, you can use any variable, for example h, and say that the derivative is the limit of this expression, but then this h can be any variable. It doesn't need to be special variable, because lim notation makes it into the shrinking variable. Okay, let's continue. Of course, you can always stop me, you know. I get very concentrated. Maybe I look scary to you, so you don't want to interrupt, but please do interrupt. I would really appreciate it. Now, I told you, yeah, derivative, strange fictitious variable. It has certain properties that we expect for it, but how do we construct it mathematically? Yeah? How do we use the mathematics of the time to construct it? How can we describe it? And the best way, and the most precise way actually, is by using algebra. Yeah? So we have the function, for example, t squared, which is this one. And this function has a specific shape, so for each input it kind of doubles it, actually it squares it. And then let's see how can we implement this special infinitesimal, this special quantity, this fictitious quantity. First of all, yeah, here is our expression. We will use the limit expression. And anytime you see a limit of the expression, you just know that it is asking, what does this thing approach as dt approaches 0? So that's all it asks. It doesn't ask what it is, it asks what it approaches. So it has a specific question in mind that it asks you. And when you answer what the derivative is, you need to answer the question, what does it approach, not what it is. Yeah? Okay, keep that in mind. Okay, now we have s of t equals t squared. S of t equals t squared, and what we need to fill is s of t plus dt minus s of t. So we need to replace it. So s of t, we know what it is. S of t is t squared. What is s of t plus dt? So whatever is inside, whatever it is, if it's 5, it gets 25. So whatever it is becomes that times itself, or squared. So then it would be t plus dt squared. Okay, divided by dt. So this is an expression that can help us to find what the true derivative is. Yeah? How do we do it? You simply expand this t plus dt squared. You get t squared plus 2t dt plus dt squared. This you know from school, like elementary algebraic operations, minus t squared over dt. So far, so good. Everything looks like the old, plain good old math that we know. If we distribute dt, we can take it in front of the expression. Another very simple algebraic operation. Because 2t squared and t squared, these are some numbers. Yeah, we can just cancel them. And now the interesting thing is, can we do this? Can we cancel dt, which shows up in the denominator, with the dt that shows in the numerator? Can we cancel them? Can we do this operation? Huh? You would cancel them. If it was 0, would you be able to cancel it? If dt was equal to 0, would you be able to cancel it?
0 or 0 doesn't exist.
Exactly. So 0 is undefined. If it was 0, so we want something variable. And we said it's not 0. If it's not 0, then we can cancel it. Because you can cancel if you have an expression 15 over 3. Yeah, you can cancel it. Is equal to 5. Because this is equal to 3 times 5, and this is equal to 3. You can cancel it and get 5, yeah? And because this thing is not 0, it's never going to be 0. It's always going to move to 0, but it's not 0. You can cancel it. So this is how you implement, this is the first thing that you implement in this new kind of calculus, yeah? You can cancel it from the numerator and denominator. So when you cancel it, you are just left with the limit of 2t plus dt. And then what is this expression asking you? Is it asking you what 2t plus dt is? No. It is asking you what does 2t and dt approach as dt approaches 0. And as you know, as dt approaches 0, the whole expression approaches 2t. So these two operations, interpretation of this last step and the cancellation of dt, this makes it possible to actually create this variable in mathematics which is bigger than 0 but smaller than any kind of feasible measurement. So this trick, yeah, you kind of say in front what you want from it, and then what you want, you implement it by following the reasoning. So it cannot be 0, therefore cross it out. And then you get what? That the derivative of the function y is equal to s of t is equal to t squared. We get the derivative ds over dt equals to 2t. Yeah? Or you can write it in this way, but I don't like this way. You can say s prime of t equals t squared, or 2t. Yeah? So this is a function. The input thing is a function. And the output thing is also a function. So the derivative maps one function to another. Another function is the derivative of the input. Yeah? As I said, input, output. Input is the red one, output is the blue one. And the derivative is what maps the values. Which means that if you're interested at the speed, which is at 3 seconds after the start, you just go to 3 here and see what is the speed at that point. Yeah? It will be 2 times 3 equals to 6. So you can now predict, actually calculate, the speed at any point if you know a function, which is it can be any kind of function, for example, but let's say that it's about speed, so that it kind of relates time and distance. It can have any kind of graph. If you're able to find the derivative, you know at each point of time what the speed is. This is what derivative gives you. It's kind of useful in this context, but I will then show you how it is useful for many, many, many things. Okay, now I showed you the algebraic trick. Let's now see another perspective, geometric perspective of derivatives. Let's see what derivative means if we think about geometry. Okay? We have a function again, x squared, f of x is equal to x squared. It's not anymore s of t, because I don't want to say that it's about space and time or whatever. It's just a function now, yeah? Any kind of relationship between x and y. And now we say, okay, it's x squared, which is again the parabola. And I want to show you that there is a specific geometrical way that we can think about multiplication or squaring or about squaring a function. For example, x squared means, of course, it has multiple meanings. What it means, it doesn't mean always this, but definitely also means this, is equal to x times x. And then, of course, x to the fourth would be x times x times x times x. So how many times you multiply the thing by itself. Okay. What is x times x if we think about geometry? Any product in geometry, we can think of it as an area. For example, if you have a rectangle with the sides a and b, the product will be area equals a times b. Yeah? So we can also think about this x squared as a product of the thing with itself. If we move x in the input space, we get x in one direction and x in another direction, and their area that this encompasses is equal to x squared. Yeah? And then let's say that we added this small value, which is called infinitesimal, or we call it dx. Yeah? we add it to the input space. What it does is create some additional area, which was not there before. So you have the light blue area of x squared, and you see something around it now, yeah? This is what derivative added to the area. Okay. Let's see it more closely. What the derivative here is this added area, this purple area, divided by what caused it. And what caused it is this distance of dt, in this case, yeah? So it is an area divided by a length. So area, and to find this area, you just simply need to multiply these widths to get what's the area. So for example, the upper rectangle is dt times t, yeah? And then the right rectangle is, again, dt times t. So it's 2t dt, 2 times t dt. And then we add this dt squared. And then we divide it, so this is this area, we divide it by what caused it, which is dt. And now we imagine that this t kind of starts shrinking. And not that it's just starting shrinking, it's just that it's always shrinking. So it's not really, this is now of course too big. It's something imaginary, but you can imagine it, that is some kind of super small area. And then you get the kind of the same expression that you would get if you did algebra. It's really the same expression. So if you divide it, you will get that the derivative is again 2t, as we said here. But what are these 2t's? These are these two lengths of the edges. So one left edge and the bottom edge. Left edge and the bottom edge is the derivative. So derivative, in geometrical sense, is some kind of residue of geometry. If you have certain geometry in certain dimensionality, derivative would be a lower dimensionality residue. So it's not you cannot express it as an area because it's length. But it's the length which is attached to this area. Okay, interesting. Let's see another example. What is the derivative of a cube? So of a function which is x to the third power. So x times x times x. If we think about it, what it means geometrically, it's a volume, yeah? Volume of a cube. In the next step, let's add dx. As we add dx, this volume grows a little bit, yeah? Of course, I'm exaggerating here. So what you get 3 of these blue parallel pipettes. Each of them has volume x times dx times x. And then you get these purple ones, which are dx times x. And then you get one small cube, which is dx to the third power. Yeah? Show these additional areas. You can see them here. So the derivative is all of these areas divided by what caused them. And what caused them is this dx, this one small length. So all this volume divided by this length. Try to express this in terms of algebra. You can get these 3 expressions, which one is for the blue ones, one is for the purple ones, and one is for the green ones. All that divided by what caused it, which is dx. And now, dx squared. That is interesting. If we think about what dx is, so if you have a length, and if you add dx, you will know that this dx is infinitely small in relation to any length, yeah? Whichever length you have, if you add dx to it, this is infinitely small in terms of this length. If you have dx squared is infinitely small in terms of the dx itself.
So it's an infinitesimal of an infinitesimal.
So you can kind of discard it. If you ask what it approaches, it's going to disappear. And dx cubed,
it's going to be an infinitesimal of an infinitesimal of an infinitesimal.
It's just going to be so small that it will simply disappear. So in this case, we can just discard them. Because they, in terms of the blue ones, they are too small to matter, yeah? And then when you ask, what does this approach as dx approaches 0, as this 3x squared? So again, it's a residue in a lower dimension of the initial geometry. So the derivative definitely has some geometrical meaning. I'm not saying that the geometrical meaning is primary or the algebraic one is primary. I'm just saying that there are many faces to this concept. And I think it's better if you know more, because then you will actually remember it better, what it is about. You do not have to have one perspective towards these things. Now, let's see how can we operate it with these derivatives. We know how to find them, but in principle, if we create any kind of computation, or if we build models, these models are not going to be y is equal to x squared. They're going to be some kind of manipulation of different functions. They're going to be multiplying one function with another. There will be composition of functions. So I will just like to do a short review, if you do not mind, of what functions are about and how can we combine them. So if we think about function, they are very specific mathematical objects. For example, this is f. And then we go from left to right. This is the input. And this is the output. So if you have something in the input, function assigns an output from it. Yeah? So for one input, there can be only one output. This is what function definition of the function is limited to. Yeah? For one input or multiple inputs in the same function, there can be only one output associated with this input. And when you think it in terms of a graph, like x squared, if this is x and this is y, and this is y equals x squared, then the input is on this axis, yeah? So this is input. It can be measured whatever you say. This is the current value of the input. For this value of the input, which is this, output is this. So the length until it crosses the graph. So this is input, output. And then this graph shows you the relation between them, yeah? If it's linear, or if it's quadratic, or whatever, yeah? But what do we do with functions? In programming, functions, we use them all the time, we create them all the time, and usually they're not simple functions. They encompass some mathematical operations. For example, one thing we do with functions is function addition. So we have one function which is, for example, f of x equals x squared, and we have another function which is g of x equals 3x. Yeah? So x is the input, and for example, because I describe everything in terms of x, now I can ask what is f of x plus g of x. So what is the sum of these two functions? So because I'm asking this, in this expression I'm coupling, both of them have x, so this means that they are dependent on the same input. Yeah? So they have the same input here, but there are two curves. One is x squared and one is 3x. So if this is the input, then this is the output of the x squared, and this here is the output of the 3x. Of course, this is wrong. I mean, how it is written here, how it is graphed. Yeah. And then the output of these two, of f of x plus g of x, will be just, for the same input, you just add the outputs, this output plus this output, which will just lift this one here, and it will give you the point in which, for the input, you get f of x plus g of x. And now you imagine, you do it for each input, you just add both of them. So here you add this and this, here you subtract this from this, and you get some kind of curve, which will be then f of x plus g of x. Okay, easy. Then let's see what is function multiplication. So if we have again f of x equals x squared and g of x equals sine of x, for example, the question is what is f of x times g of x? And as I showed you in the geometrical perspective to derivatives, we can think about multiplication as what? As an area. So let's now imagine we have two functions. One is x squared and one is sine of x. So for the same input, for example, x, whatever it is, this is the output of the first one, and this is the output of the second one. And this area is f of x times g of x. And then there is one more operation, and then we are done with them, then we see what derivatives are doing to them, is function composition. So we will see this in detail. F of x is, for example, x squared, and g of x equals sine of x again, but it can be anything. And we can ask what is g of f of x. What does this mean? If we have a function here, which is, for example, f, which maps input to output, which maps this length to this length, yeah? What is g of f of x? It's simply two of these boxes. So one is f, and one is g. So then we have an input, and then this input, for example, of f of g of x, which is sine of x, has an output. So this is now temporary output, yeah? Temp output. Why temp? Because it becomes an input for the next one. And then there is an output. So for one and the same input, this one change it in a certain way, and then this becomes input for the next one, which changes it in a certain way. And this idea, we can think about is as modulation, if you heard this word. Modulation. So G is modulating F. And I will now want to show you what does this mean. This is very important in music, because in music we work with modulation a lot. Okay, and now I want to just show you animated examples of these operations, and then question what happens when we ask for a derivative of this addition, when we ask for a derivative of this multiplication, and when we ask a derivative of this composition. So that's what I want to show you today, and then we are done. Okay, function addition. So you have green line, which is f of x, you have blue line, which is g of x, and you have red line, which is actually already pre-computed, f of x plus g of x. So what I told you is that output of green plus output of blue is what makes output of red. So if I move x, you can see that these three lines on the top make up, when you add them or subtract them, the red one. This is the meaning of function addition in geometrical sense. Yeah? And now the question is, what happens when you add derivatives to the story? What is the derivative of this sum? I will just go quickly through it because this is not, it is just important to kind of see it once or twice. You do not have to remember the formula, I will not ask you for that. It's just for you to understand then how do derivatives work. So there you have it. You have, again, green and blue, which are two functions that we add into the red one. And as you can see, if you add x plus dx to all of them, because the x is the same for both functions that we add, this means that dx is also the same for the both functions that we add. And we can see that we have three triangles, and that the height of or the output of the derivative will be a sum of the outputs of its constituents. So the derivative of this sum, I think I have a formula, will be the sum of the derivatives. Derivative of the sum is equal to the sum of the derivatives. So you simply add the output of one, derivative of one, plus derivative of other, and that's it. Nothing more than that in the derivative world and the sums. Okay, multiplication, I gave you an idea that multiplication is about areas. We have the x which we're gonna move, and this x will give us its output on the vertical axis, and then from these outputs on the vertical axis, we will construct an area. And there you go. As you can see, this area changes with the input. And then again, we just add a small dx to the input. There's infinitesimal as a result of the output of the first function, and the infinitesimal as the output of the second function. And they are not the same. And this is very interesting. Infinitesimals, although they are these quantities that approach zero, they do not approach zero with the same speed. One can approach it faster, one can approach it slower. If we have a function x to the 100th power, the infinitesimal that approaches zero will do it very quickly. If we have a logarithmic function, this derivative will approach zero very slowly. So therefore, these imaginary quantities can have different speed, and this speed is then can be, speed, it's not really speed in the traditional sense, but they have different magnitudes, and they can be read, for example, in geometrical sense. Let's now just see what the derivative here is. As I told you, the derivative is, in the geometrical sense, is now this additional area divided by what caused it. And what caused it is dx, yeah? So we need to simply multiply the things that we see on the screen and divide them by dx. So as you can see, the top one is sine of x plus d of x squared. The right one is x squared times d of sine of x squared. And the one on the right, top right, is d of sine of x times d of x squared. Yeah? And then you can represent this as a formula. And you can say, okay, you need to memorize this formula. And in school, probably they teach you to memorize this formula. And what I'm trying to show you here is that really there's no need to memorize it, because you can just draw this sketch and just calculate it in 5 seconds what it is. So the derivative of a product is, you can see it here very, very quickly, is the first element of the product times the derivative of the second one plus the second one times the derivative of the first. But this formula can be daunting, and actually what happens here, if you think about areas, is very simple to calculate. And now the most important thing, and something that we use in computation all the time, is we stack functions. Yeah? Function composition, this thing here. And now I'll try to give you some animations for you to better understand what this composition, how does this look like. So you have 4 functions here, and they are all functions of the same kind of inputs. So some x, which can be something, some value on a number line. Let's say it's a number. And then they all have their outputs, but they're different. Yeah, different functions, not the same. Otherwise, they will have the same name. Let's now chain them. Let's just plug the output of each one into the next one. So if we chain them, then we have a single input and a single output, and this output will be modulated by this chain. Yeah? Each of these components will change the next one a little bit. It will modulate the whole thing. Yeah? This is how we can express it. It's ugly, but this is how you would do it algebraically. So output is k of h of g of f of input. That's how you would represent it mathematically. Okay. Let's try to somehow visualize it. We have, for example, input, and then we have 1, 2, 3 middle stages, and 1 output. And let's just then make 5 number lines and see where the input, how does input relate to the next output, then how does this next output serve as an input for the next one. Let's see what happens if we change the input. You see, as we change the input, I'm not telling you what the functions are, it's not really important. The chain starts moving in the y direction. It means that the output is modulated through all of these stages. Yeah? And again, as I showed you before, with the derivative, if you want to visualize it in any kind of way, what you need to do is at whatever point in time or whatever point you are of this phenomena, you just need to add an infinitesimal to it and see what happens when you add it. Yeah? So I'm now adding an infinitesimal, you see? And the interesting thing is that if I add the infinitesimal to the input and call it the input, yeah, to say that it's a small quantity which is always going towards 0, you will say that this will cause the other variables to reproduce their own infinitesimal. So there will be infinitesimal of each of these outputs and inputs. And finally, there will be the infinitesimal in the output. And this is very interesting because it shows you that the lengths of these, although these quantities are infinitely small, they are not the same. So they are kind of fictitious magnitudes which differ from each other, and all of them have the same property that are larger than 0 but smaller than a feasible measurement. And now, as I move the input, you will see that also they change depending on what the input is. As you can see, as the input and output changes, they change too. So they are not fixed. Okay, and now, as I said, the output is k of h of g of f on input. The question is, what is the derivative, or what is the change of output in terms of small change in input? So we can write this as the output over the input. And how we compute it, not only what it is, I mean, it is what it is, it's just literally the ratio of these two things. How do we compute this thing? So if you have a long chain like that, you can imagine that computing it might be difficult. And chain rule is a certain property of derivatives and the property of composition that allows you to make this computation much, much easier. And because of this chain rule, only because of this chain rule, we actually can have neural networks, for example, or deep learning. Because if we wanted to actually find the derivative of the output to the input directly, this would be impossible, because machine learning is a function of, for example, 15 million inputs, 15 million variables. It would be impossible. Chain rule allows us to somehow decompose this input and output ratio. Now let's see how we can do it. If we want to decompose it, we can say that the output length divided by the input length is equal to the output divided by d of h times dh divided by dg times dg divided by df times df divided by the input. So as you can see what I did, instead of having one large derivative to process, I have now 4 expressions, 4 derivatives, which are much simpler to calculate, and I can just multiply them together as if they were a chain to find a very complex derivative, which is the output over the input. Also, interesting thing is that because these middle steps are not necessary, they can be crossed out. So as you can see, I can cross everything out and again finish with the output over the input. But not crossing it out will significantly help me to actually compute it. Okay, this is not the only way how I can do it. I can decompose it, for example, in this way. The output over dh times dh over the input. If that's easier for me to compute, I can do that. Or I can do it like this. The output over dg, dg over the input. So as long as I'm not skipping anything, I can do it whatever I want, but this is the most common way. This is usually the easiest way to compute the derivative. And I will now show you a simple example of how this actually works. How can we compute it with the chain rule? So we have one function which is x squared, which is parabola that I showed you. And we have a sine function, sine of x. And now let's chain them. Now we can describe y in terms of x. For example, y is f of x and it's equal to x squared. You can describe z in terms of y. For example, you see z is g of y, which is sine of y. Or you can then do the whole thing and say z in terms of x, which is z is then equal to g of f of x, or sine of x squared. So we had x squared and sine of x, now we have sine of x squared. This is the chain that we made. Okay. And now, what I told you is that x squared now modulates the sine function, or modulates the output. It kind of messes up with its oscillation period. And this is the graph. As you can see, this kind of differs from the classical periodic function, which is sine x, because you can see that the period is constantly changing. As we go further away from the origin, the period becomes smaller and smaller. So as if somehow x squared is changing the speed of the oscillation. And I will show you now actually how this happens. Here you have these two functions, and we have the same x. As you can see, if I change x, now you have 3 number lines there. As the output of x gets larger, this one starts moving faster. I can repeat it. So x squared, as it goes further away, it starts modulating the speed of the oscillation of
sine of x.
This is how this thing is constructed. Let's just stop this in a certain moment of time, and then let's see what's going on there. We have x up there, which then gives us the output, x squared. Then this x squared, this green dotted line, you can see it here, and you can see it there. This line now becomes an input for the sine of x. And for this input, it produces the red line, which is the output, sine of x. And then this output, sine of x, is here. And now the question of the derivative is, again, the same thing. What happens when we change the input for a tiny, tiny amount? When we add the infinitesimal. And when we add it, you can see that we add dx. Then dx causes an infinitesimal of the output of the x squared, which is then d of x squared, which is the green line. And then d of x squared changes the input of this function and causes the output
d of sine of x squared.
So we're always doing the same procedure to all of these operations. Yeah? And now, let's try to see then what is the derivative here. And as you can already imagine, the derivative is simply the red line over blue line. So the length of the red line divided by the length of the blue line. And you already know that they are not real lines, they're shrinking magnitude. And they shrink at the same time at different speeds. Okay, so it's dg over dx, blue, red over blue. But how can we compute it? It's a little bit complicated to compute d of sine of x over dx. How can we simplify this? And this is where chain rule comes from. We can decompose this into looking at the ratio of the red line over green line times the ratio of the green line over blue line. So we decompose this output-input ratio with this middle step. And now we have two derivatives to compute, but they are kind of simpler. So we have d of sine of x over x squared, and we have d of x squared over dx. And this one we already know. This is just the derivative of the x squared, which is, I don't know where I computed, it's just 2x. Yeah? And this one, d of sine of x squared over x squared, this looks a little bit complicated, but if you think about it, x squared, we can just symbolize it as any kind of variable. We can, for example, call it y. Y is equal to x squared. And then the question is, what is sine of y over d of y? And if you look at the derivative tables, you will see that the derivative of sine function is cosine function. So it's cosine of y times 2x. And then now we can, since we said that y is equal to x squared, we can just replace it with cosine of x squared over 2x. And now we have the derivative. The derivative of our chain is cosine of x squared times 2x. And here you can see these two functions intertwined. The green one is the input and the blue one is the output. I want you to now see the relation between the blue curve and the green curve. The interesting thing is, when the function reaches its minimal states, for example, when the green curve has its minimal or maximal states, you can see that the blue curve indicates something. And let's see what it does actually. If we zoom in, and if we investigate these values at the top and at the bottom, you will see that they land on a spot where the derivative function is equal to 0. And it does so both for the minima and for the maxima. So the derivative function is very useful because it tells us about some kind of terminal states of our function. And we will use this property to actually construct some machine learning model, because this is the property that allows us to do so. Okay, and then next class we will have application of derivatives. I will show you how to use derivatives to actually do exactly that, and how from derivatives we can devise the notion of optimization, because this is what they are used for. And then we will continue further. Okay, that's it for today, and thanks. If you have any questions, please, you can ask me after the class.